Poly-lactic acid, or polylactide is a biodegradable thermoplastic aliphatic polyester derived from renewable resources, such as corn starch, tapioca roots, chips or starch, or sugarcane. In 2010, PLA had the second highest consumption volume of any bioplastic of the world. The name polylactic acid does not comply with IUPAC standard nomenclature, and is potentially ambiguous or confusing, because PLA is not a polyacid, but rather a polyester. Production: there are several industrial routes to usable PLA. Two main monomers are used, lactic acid, and the cyclic diester, lactide. The most common route to PLA is the ring-opening polymerization of lactide with various metal catalysts in solution, in the melt, or as a suspension. The metal-catalyzed reaction tends to cause racemization of the PLA, reducing its stereoregularity compared to the starting material. Another route to PLA is the direct condensation of lactic acid monomers. This process needs to be carried out at less than 200 degrees Celsius. Above that temperature, the entropically favored lactide monomer is generated. This reaction generates one equivalent of water for every condensation step, and that is undesirable because water causes chain transfer leading to low molecular weight material. The direct condensation is thus performed in a stepwise fashion, where lactic acid is first oligomerized to PLA oligomers. Thereafter, polycondensation is done in the melt or as a solution, where short oligomeric units are combined to give a high molecular weight polymer strand. Water removal by application of a vacuum or by azeotropic distillation is crucial to favor polycondensation over transesterification. Molecular weights of 130 kDa can be obtained this way. Even higher molecular weights can be attained by carefully crystallizing the crude polymer from the melt. Carboxylic acid and alcohol end groups are thus concentrated in the amorphous region of the solid polymer, and so they can react. Molecular weights of 128 to 152 kDa are obtainable thus. Polymerization of a racemic mixture of L and D lactides usually leads to the synthesis of poly-DL lactide, which is amorphous. Use of stereospecific catalysts can lead to heterotactic PLA, which has been found to show crystallinity. The degree of crystallinity, and hence many important properties, is largely controlled by the ratio of D to L enantiomers used, and to a lesser extent on the type of catalyst used. Apart from lactic acid and lactide, lactic acid O-carboxyanhydride, a 5-membered cyclic compound, has been used academically as well. This compound is more reactive than lactide, because its polymerization is driven by the loss of one equivalent of carbon dioxide per equivalent of lactic acid. Water is not a co-product. The direct biosynthesis of PLA similar to the poly-hydroxyalkanoate, S, has been reported as well. Manufacturers: as of June 2010, NatureWorks was the primary producer of PLA in the United States. Other companies involved in PLA manufacturing are PURAC Biomaterials and several Chinese manufacturers. The primary producer of PDLLA is PURAC, a wholly owned subsidiary of CSM located in the Netherlands. Galactic and Total Petrochemicals operate a joint venture, Futero, which is developing a second-generation polylactic acid product. This project includes the building of a PLA pilot plant in Belgium capable of producing 1,500 tons a year. Chemical and physical properties: due to the chiral nature of lactic acid, several distinct forms of polylactide exist. Poly-L-lactide is the product resulting from polymerization of L-lactide. PLLA has a crystallinity of around 37%, a glass transition temperature 60–65 AA degrees Celsius, a melting temperature 173–178 AA degrees Celsius, and a tensile modulus 2.7–16 GPa. Heat-resistant PLA can withstand temperatures of 110 AA degrees Celsius. PLA is soluble in chlorinated solvents, hot benzene, tetrahydrofuran, and dioxin. PLA has similar mechanical properties to PET polymer, but has a significantly lower maximum continuous use temperature. Polylactic acid can be processed like most thermoplastics into fiber and film. the melting temperature of PLLA can be increased by 40 to 50 degrees Celsius and its heat deflection temperature can be increased from approximately 60 degrees Celsius to up to 190 degrees Celsius by physically blending the polymer with PDLA. PDLA and PLLA form a highly regular stereocomplex with increased crystallinity. The temperature stability is maximized when a 1:1 blend is used, but even at lower concentrations of 3 to 10% of PDLA, there is still a substantial improvement. In the latter case, PDLA acts as a nucleating agent, thereby increasing the crystallization rate. Biodegradation of PDLA is slower than for PLA due to the higher crystallinity of PDLA. There is also poly-lactide co-D, L-lactide, used as PLDLLATCP scaffolds for bone engineering. Applications: PLA can be processed by extrusion, injection molding, film and sheet casting, and spinning, providing access to a wide range of materials. Being able to degrade into innocuous lactic acid, PLA is used as medical implants in the form of anchors, screws, plates, pins, rods, and as a mesh. Depending on the exact type used, it breaks down inside the body within 6 months to 2 years. This gradual degradation is desirable for a support structure, because it gradually transfers the load to the body as that area heals. The strength characteristics of PLA and PLLA implants are well documented. PLA can also be used as a compostable packaging material, either cast, injection molded, or spun. Cups and bags have been made from this material. In the form of a film, it shrinks upon heating, allowing it to be used in shrink tunnels. It is useful for producing loose fill packaging, compost bags, food packaging, and disposable tableware. In the form of fibers and non-woven textiles, PLA also has many potential uses, for example as upholstery, disposable garments, awnings, feminine hygiene products, and diapers. Racemic and regular PLLA has a low glass transition temperature, which is undesirable. A stereocomplex of PDLA and PLLA has a higher glass transition temperatures, lending it more mechanical strength. It has a wide range of applications, such as woven shirts, microwavable trays, hot fill applications and even engineering plastics. Such blends also have good form stability and visual transparency, making them useful for low-end packaging applications. Pure polylactic acid, on the other hand, is the main ingredient in Sculptra, a long-lasting facial volume enhancer, primarily used for lipotrophy of cheeks. Progress in biotechnology has resulted in the development of commercial production of the D enantiomer form, something that was not possible until recently. PLA is also used as a feedstock material in 3D printers. The properties enable PLA-printed solids to be encased in plaster-like molding materials, then burned out in a furnace, so that the resulting void can be filled with molten metal. This is known as lost PLA casting, a type of investment casting. Recycling. Currently, the SPI resin identification code 7 is applicable for PLA. In Belgium, Galactic started the first pilot unit to chemically recycle PLA. Unlike mechanical recycling, waste material can hold various contaminants. Polylactic acid can be recycled to monomer by thermal depolymerization or hydrolysis. When purified, the monomer can be used for the manufacture of virgin PLA with no loss of original properties. Degradation, amyloidopsis and saccharotrix are able to degrade PLA. A purified protease from amyloidopsis sp, PLA depolymerase, can also degrade PLA. Enzymes such as bromelain, Pronus and most effectively proteinase K from Tritium album degrade PLA. Pure PLLA foams undergo selective hydrolysis when placed in an environment of DMEM supplemented with fetal bovine serum. After 30 days of submersion in DMEM plus FBS, a PLLA scaffold lost about 20% of its weight. See also, cellophane, metallic glass, plastarch material, polycarprolactone, polyglycolide, poly-3-hydroxybutyrate, zein, 3D printing, acrylonitrile butadiene styrene, Ultimaker, MakerBot, references. External links, new polymerization technology for PLA developed, white paper on the science of biodegradable plastics, FP International, Your Plastic Pal, The Economist article, comparisons and LCA cycle of PLA in solution, in the melt, or as a suspension. The metal-catalyzed reaction tends to cause racemization of the PLA, reducing its stereoregularity compared to the starting material. Another route to PLA is the direct condensation of lactic acid and highest consumption volume of any bioplastic of the world. The name poly-lactic acid does not comply with IUPAC standard nomenclature, and is potentially ambiguous or confusing, because PLA is not a polyacid, but rather a polyester. Monomers. This process needs to be carried out at less than 200 degrees Celsius. Above that temperature, the entropically favored lactide monomer is generated. This reaction generates one equivalent of water for every condensation step, and that is undesired production. There are several industrial routes to usable PLA. Two main monomers are used, lactic acid, and the cyclic diester, lactide. The most common route to PLA is the ring-opening polymerization of lactide with various metal catalysts, and poly-lactic acid, or polylactide is a biodegradable thermoplastic aliphatic polyester derived from renewable resources, such as corn starch, tapioca roots, chips or starch, or sugarcane. In 2010, PLA had the second